Yeah, hello everyone. Thank you for the invitation to present at this conference. Let me see. Okay. Can you see my screen?
Yes.
Okay, great. Again, thank you for the invitation to present at this conference. And, I'll try in this brief talk to give you an idea about the potential of emerging electronic-photonic integrated systems as a platform of CMOS technology that can address a variety of applications, starting from interconnects that accelerate AI, which is obviously one of the very hot topics in hardware industry today, to more exotic things that are as equally applicable, for example, like biosensors and, acute to us as an example of COVID-19 sensors. A little bit of a perspective on last quarter century of integrated circuits. Recently, we've started talking about the slowdown in Moore's law and trying to figure out how various technologies can help with that. Packaging presentation before me was really informative and showing that convergence of various chiplets and functions. But if we go back in history and see, people have always been trying to add additional functionality to a CMOS process to make it better. Starting from early years where Nguyen and Meyer were experimenting with thick metal wires to create inductors to enable CMOS radio applications. And we all know what happened after that. We had a mobile radio revolution. The early experiments in adding transmission lines to ICs in Berkeley Wireless Center by Nick Najad and Brodersen around 16 years ago led, of course, to creating millimeter wave radios and phase arrays and things like that we now take for granted in 5G and the next communication set of standards. Similarly, following the same philosophy, my team, including Professor Popovic and Ram, have looked at how we can add photonic component functionality to an existing high volume manufacturing CMOS process. Because led by the previous examples, we knew that if we are able to do that in a CMOS process, we will be able to unlock significant new applications that we can utilize with this technology. So in 2012, we demonstrated for the first time full monolithic integration of transistors, photonics, and photonic components in 45 nanometer SOI process. At that time, that was the leading process for, let's say, IBM's power series processors, the cell processor, etc. And pretty quickly after that, because we were in a high volume manufacturing process, without changes to the transistors, we've been adding these photonic components and enabled a pretty high level system demonstration. This was the world's first processor to communicate with light. So we've been able to, together with Professor Asanovic at Berkeley, we've been able to integrate two RISC-V vector cores into the chip, add a photonic memory interface, and be able to talk between the two processor and memory chips, use and run applications running over this embedded silicon photonics. Now, of course, that was as close and practical presentation as we could do from the university environment. So after that, we spun out two companies. One was Sci5, which was looking to commercialize the RISC-V processor designs and ecosystem. And another company was Ayar Labs, where we were trying to set up the stage to commercialize these optical I/O photonic chiplet technology. The key device that you can potentially see here as kind of a very tiny device on the chip next to the circuits is the so-called ring resonator. And this device is really like 10 micron in radius and much, much smaller than any other comparable type of photonic device that people would use, let's say in pluggable optics interfaces like Mach-Zehnder, and allows you to be able to create very large scale integration electronic photonic circuits. But it has its issues and requires circuits and control to be able to stabilize it. This is a ring resonator that couples the light that comes on the incoming waveguide. And when it resonates at the wavelength of the incoming light, it creates this notch filter. So it basically traps the light. And by changing the index of refraction of this, this is effectively a PN junction around the silicon ring, you can actually inject the carriers and then provide the shift. You can also heat the ring resonator with an internal heater, and then also be able to provide a thermal tuning shift that compensates for the environmental or process variations. Similarly, you are also able to embed germanium or silicon germanium. In this case, we use the SIGI that exists in the transistor of this process to create a photodetector, because now you create an absorption region where the incoming light at a corresponding wavelength can actually get trapped and get absorbed into a charge. And with that, we can create very dense wavelength division multiplex systems where each one of these rings in a wavelength division multiplex bus can actually modulate its own separate laser wavelength. And that way we can carry hundreds of gigabits per second toward terabits per second on a single piece of waveguide, or coupling outside into the fiber. Now, of course, to be able to utilize these devices, you need circuitry around them to stabilize them temperature-wise, to modulate them, etc. And that's where this monolithic integration comes very handy. That's what we've been doing in this processor demonstration, but also more commercially in Ayar labs. So now, with this technological capability, we're looking as to how we can address the technological trends that are around us today. It was a very informative at Hot Chips this year to be able to see the focus of the industry on the scale out in AI. And that's driven by the tremendous progress in the application space in AI. I'm just showing you here a Google slide from the scale out where they've shown that in the last year and a half, we've gone from the state-of-the-art transformer language models to multiplicity of experiment language models, where the size of the model has increased 3 orders of magnitude. 3 orders of magnitude bigger size requires 3 orders of magnitude bigger computation and 3 orders of magnitude bigger memory. And this slope has been much bigger than the slope of about 2 orders of magnitude every 2 years that has happened previously with image classification algorithms from AlexNet to, let's say, ResNet or other more sophisticated image classification algorithms. This slope is what drives hardware industry to be able to try to somehow make it up. And of course, what you see nowadays is that there are new supercomputers emerging. Google, this is again a Google slide from Hot Chips where they effectively state that the space race is on for the biggest ML machine. You have Microsoft building AI supercomputers for OpenAI, NVIDIA building the Cellen computers and superpods as modular appliance solutions that other data centers can start applying to shift their infrastructure from very generic server-based into more of a AI-tailored supercomputing. Google was already offering the services through their multi-pods, and we're talking about somewhere between a couple thousand and 10,000 GPU chips per these, or accelerator chips per cluster. That's kind of roughly the size of these systems. And what's interesting to see is that this is again an excerpt from the multiplicity of experiments, this largest training model that Google has deployed, that as you replicate the training pipelines, this is one experiment, this is the nth experiment, there is a layer where all of these have to talk to each other. And that, if you look at their benchmarking, as the number of experiments is increasing, the computation pretty much stays the same because you can parallelize that across multiple clusters. But the component that grows tremendously is the interconnect, this all-to-all dispatch piece. And this already at an order of about 2,000 experiments, which is 4,000 TPU chips, you're already seeing a third of the overall runtime being consumed by the fabric. And there's not a lot of room to grow from here before you're completely consumed by this communication time, right? So the time is for a new interconnect or new technology that helps to alleviate this bottleneck. So if you look at the landscape of AI, in the early years, it was focused on small 8 to 16 GPU type of boxes. These are like DGX-like fabrics with a couple of terabits between GPUs, but very small GPU deployments. The most recent ones that I was describing are in the order of a couple thousand to 10,000 GPUs, but connected with even lower InfiniBand bandwidths from shelf to shelf. What we need for these systems to be able to catch up with the application developments of, let's say, 3 orders of magnitude in the next couple of years is to add many more nodes and improve the speed of communication from each one of the nodes, from a couple of terabits per second to tens towards 100 terabits per second. And the question is, how do we do that without compromising the latency and parallelism of this model computation? The interconnects, of course, are a key component there. It's useful to see what are their metrics and how do they impact this type of scaling. So I'm plotting here bandwidth density and energy efficiency, which are 2 key metrics in the interconnects. And what you see at a very high level is that if you go from in-package interconnects, let's say like HBM, all the way down to off-board, where the only solution right now is really the pluggable cross-rack and multiple racks, optical pluggable, you see 3 to 4 orders of magnitude gap in these bandwidth density and energy efficiency metrics. So you need an interconnect solution that's able to bridge this gap and allow you to communicate anywhere in the system at the cost of in-package interconnects. If you're able to achieve that, then you can enable this type of seamless AI and computation scaling, right? So one of the first enabling technologies for that is the Optical I/O that I mentioned previously. We've demonstrated on the research side. And this is kind of one of the recent demonstrations that Ayar Labs has done with Intel, where they co-package their chiplet. This is an Optical I/O chiplet that is similar to this one I showed you earlier, where you have CMOS transistors and photonic components, basically optical SerDes, that is co-packaged with the Stratix 10 SoC using an EMIB 2.5D packaging technology. And you've heard a little bit about that kind of in the previous talk as well. It's an embedded silicon bridge that provides a very low speed, wide parallel interface between the die, but then the optical I/O serializes this output in a very energy efficient way. Now, this is roughly the architecture of that interconnect solution, where you have the host SoC in the package, you have the optical chiplet, which has both circuits and optical devices. Because of that monolithic integration on the chiplet, you're flexible to implement whatever type of electrical I/O interface in package the host SoC prefers, whether that's wide parallel, like AIB or HBM or HBI, or it's a high-speed serial. That will determine the complexity of the package, as we've seen previously, but it will enable you either way to communicate for longer lengths, centimeters to kilometers, seamlessly with high bandwidth density and energy efficiency. We remove the laser source outside of the package because the package is very hot because of the ASIC, and because we also want to enable seamless packaging, because this is just a CMOS chiplet that is co-packaged with another CMOS chip like the ASIC, right? So when you look at the back at the bandwidth density plots, the Terafy technology allows you to span this whole length range at the kind of energy bandwidth density metrics of in-package type of interconnect solutions. And that's why it's basically very appealing. Now, another enabling technology to be able to connect many nodes together is, of course, the switch. And you can have optical I/O can help provide scaling of electrical packet switches because it replaces the I/O. But ultimately, you spend a lot of power on the switches as well. And instead, we have a project at UC Berkeley with Professor Ming Wu. This is also part of DARPA Pipes, where we're building a 1024 by 1024 all optical switch. So Professor Wu designs these optical MEMS devices that can basically bridge between the two optical waveguides on a chip. We build the controller chips, and we're able to seamlessly scale the size of the switch to about 1000 by 1000 radix with a configuration times less than a microsecond, right? So with that type of a switch, you can now connect many different nodes together in a single hop or two hops up to 1 million nodes in a system, and be able to do desegregation. Have TeraPHY with a TPU or a GPU in one cluster, talk to HBM cached type of memory or DRAM on the other side of the cluster through a single hop, right? Now, those are kinds of the technologies that you can continue to build up for the applications in the interconnect space, but I wanted to give you a little bit of a flavor as to how these technologies can fundamentally be used in other applications. So in this one, we're using the same ring resonator to be able, functionalized with a protein, to be able to attract different molecular particles. And if different molecular particles land on the ring resonance will change. And if you wrap up the circuits around that ring resonator, then the circuits will be able to detect that change. And so you will be able to detect either an amplitude change in the shift of the ring resonance or the phase. And putting this in a bigger system, when you overlay the microfluidics on top of the chip, and you see the ring resonator that's functionalized with a protein, as you push the liquid through these microfluidic channels, the certain things like antibodies or RNA or even viral particles will basically latch onto this bait protein, and then the ring will be able to detect them. Because we have many rings and many multiplexed channels, we're able to simultaneously detect multiple properties of the sample, for example, saliva, right? So in this case here, we're showing effectively, a saliva sample coming in. It's going down through a microfluidic prep stage where you have certain particle beads that are pre-functionalized to filter out the stuff that's not interesting in the sample, and then release into the chip effectively only the properties that we want to detect. And then through multiplex detection, we can do different kinds of diagnostics, right? So we've already built prototypes for this using the microfluidics attached to the chip. You can see kind of the fluid going over, and then being able to, on this side, you see the light coupling in and going, and these bright spots are the ring resonators that shine essentially as they accumulate the light, and that's where the detection point is. And then we've been able, because we have circuits, of course, to do real-time detection and see different concentrations of the fluids, different binding rates of the molecules, etc. So in summary, this monolithic integration of electronics and photonics enables us to build most energy and bandwidth density efficient I/O solutions. And of course, that helps in the AI and machine learning scale out with both compute to compute and memory access as the size of the model grows and we want to be able to scale out the system. But we can also build a variety of other sensing solutions. And I've picked here molecular sensing because of the current COVID kind of relevance. But you can build also phase arrays and other types of sensors and communication devices, because after all, these optical components are just like another transmission line, just like another component in the tool set that the designer can use to build a very sophisticated electronic photonic integrated system. Thank you.